Wow, I see you got Lila. You didn't make it today. You okay?
I'm fine. There were just some things that I had to do with family.
Things you had to do. You had to leave the
Oh
country
my
and
God.
go on the lam and all that kind of stuff.
No, just a sick family member.
Oh, sorry. Okay. I'm going to start with something called, it's kind of a funky term, degrees of freedom. It's kind of a funny sounding term. It's a mathematical term. Degrees of freedom has very specifically to do with your sample size. Now, that might sound really weird. So I'm going to give you some really simple examples, okay? I'm thinking of two numbers, and my two numbers add to 10. Can you tell me what my two numbers are?
5.
Can you tell me what my two numbers are?
5 and 5.
It could be 1 and 9.
Or it could be. Oh, no. 4 and.
Negative 1,000 and 1,010. I'm pretty sure there's infinitely many possibilities. Do you agree with that? I'm thinking of two numbers, they add to 10. Can you tell me my two numbers? The answer is, of course not. Oh, I'm thinking of two numbers that add to 10, and one of my numbers is a 7. Can you tell me my two numbers? 7 and 3. Once I told you the first number, you absolutely knew the second number. But the first number could have been anything. Do you agree?
Yes.
Okay, I'm thinking of three numbers and they add to 10. Can you tell me all three of them? No. What if I told you the first one was a 2? Now, can you tell me all three of them? No. What if I told you the second one was a 4? Now, can you tell me all three of them? Yeah, you now know the third number. You knew the first two, you now automatically knew the third number. The point being, the first two numbers could have been anything, couldn't they?
Yes.
In my case where I only gave you two numbers, the first number could have been anything. But once I get down to the last number, it can't be anything. So now I'm going to give you n values, and those values add up. Pick a number. By the way, they could be anything. They could be positive, they could be negative, they could be anything. Let's use 10 again. N values add to 10. Can you tell me all of them? Assume n is large this time. Can you tell me all of my numbers? Of course not. What if I give you one of them? That's not enough. What if I gave you all but one of them? Could you then tell me the last one?
Yes.
Absolutely, every time. That's the whole point. If I have a whole bunch of numbers and you know the result of all of the numbers, but you don't know any of the numbers, you know, I keep saying things like, oh, last month, all of my receipts added to the following thing. Can you tell me what they were? No. But if I told you all of my receipts except one, then don't you automatically know the last one because you can just kind of subtract it from the whole. Does that make sense to you? Degrees of freedom is basically means all of my numbers can vary up to a point until I have one left. Then they can't, then you absolutely know the last one. So the first n-1 numbers, when there are n numbers, the first n-1 can literally be anything. But once I know the first n-1 numbers, the last number can't be anything. It's basically always going to be what is left. A simple, really simple example. You guys wrote down on a piece of paper your ages. You didn't tell anybody else. You gave it to me. I added them up. And I said, the group here, your age is 137 years as a group. Do you know the whole group? No. But if you knew 3 of the 4 people, do you automatically know the 4th person?
Yes.
So degrees of freedom, the number degrees of freedom always means one less than the sample size. And that always confuses people. Why is it n-1? Because n-1 of the numbers can be anything. But once you have the first n-1 numbers, the last number is not free, if you will, to vary. It's set in stone. There's not, it's whatever's left. So if you've thought about it that way, and I said, I want you to figure out all the numbers, you'd say it's kind of a game, but once I know all of them but one, now I know all of them. Now, you're not going to work backwards and figure out numbers. That's not the point. But in our tables have the term degrees of freedom in there. And you're going to go, why? So if I had a sample of size 30, what's the degrees of freedom? If the sample was size 30, what's the degrees of freedom? No.
Oh.
Give me a number.
Oh.
29. Yeah, you're thinking too much. If my sample's of size 30, my degrees of freedom would be 29.
Okay.
One less, because your n was 30, so n-1 is 29. You don't calculate degrees of freedom. If I tell you the sample size, the degrees of freedom is 1 less than that. And a lot of the more complex formulas If you look at your formula sheet, I don't know if you guys have it in front of you. If you look at your formula sheets, particularly for today's stuff, you see n-1. You see n-1 in there a few times. You go, and why is that? Because in the formula, a lot of times it's degrees of freedom that are calculated in the formula when there are samples. Okay, it's not for you to choose. It's like, this is the formula. Oh, that one has an n-1. Now, think about this also. This is kind of crazy. Remember the formula for variance of a population? It had an n in the denominator. But remember the formula for variance of a sample? It had n-1 in the formula. Do you remember that? I mean, go back, look at your sheet.
Yeah.
Go back to the beginning, page 1, and you see the sample variance S squared. It has an n-1 in the denominator. Oh, his simple rule of thumb. Samples generally use degrees of freedom. Populations generally use the entire n. Because in a population, the idea is you have every number. That's the whole idea of a population. I had access to every value. I had a census in front of me. But if I'm only taking a sample, the reason n-1 is used, I didn't see this until graduate school. It's so complicated, the derivation, but to remove bias, believe it or not, n-1 is used rather than n. And here's the beautiful thing. The bigger the sample is, bigger and bigger and bigger and bigger until it's getting bigger, closer to the population, the n versus n-1 doesn't make any difference from a decimal standpoint. If I got a large number and I divide it by 1,000,000, or I divide it by 1,000,000 minus 1, is it going to make a huge difference? No. But dividing it by 5 versus dividing it by 4, that might make a huge difference. So a really large sample, the n versus n-1 stops mattering. I mean, you're only going to fit way down the line on decimal places. Okay, so the degrees of freedom only apply to samples, never apply to populations. Because again, populations, you have everything. You're not taking a sample. You have all the numbers. So degrees of freedom is simply one less than the sample size. Okay, and that's easy because you're always going to know the sample size. So when we're looking up that number up in the table, so the table I just gave you, the table I just gave you, on the left-hand side, it says degrees of freedom rather than n. So that technically, if you want to just write on your table, write n-1. Where it says degrees of freedom, just right over the top with n-1, because that's what it means. So when you see 19 degrees of freedom, that meant the sample was of size 20. And so on and so on and so on.
Oh.
Okay, you work backwards and tell me where it came from. Now, what we're doing today is we want to do confidence intervals for the variance and or the standard deviation. Remember, variance is just the square of the standard deviation. Well, why would I do that? Aren't all confidence intervals mean and probability? Well, last week we did confidence intervals for probability, and we did a plus or minus. Right? We measured our probability, right? Rosalind made 80 out of 100 free throws, and we said, therefore, her true probability is going to be that number plus or minus. Because we don't know if that was a good day or a bad day or a perfect day. But we said it's reasonable that what we witnessed should be a reasonable outcome, but you might be a little better, you might not be as good. Then last day we did a confidence interval around the mean. So we used human heights. So we measured heights at Mesa College. We found the mean of our sample. Does that mean all of Mesa College is going to be that number? We didn't measure everybody. So that's kind of dangerous to say, no, I measured 15 people, so 30,000 people must be that average height. I don't think so, but that number we measured is certainly the best starting point. So what we did was we made a cushion, we calculated the error, and we did a plus or minus. And we said, now it's reasonable that Mesa is between here and here. Today, we're going to do the same thing with variance and standard deviation, but it's not a plus or minus. The reason is variance, first of all, can't be negative. Oh, I can't be on the other side of 0, in other words. Think of a z table. Aren't half the values positive z's and half the values negative z's? But variance is the square of the distance. So a simple way to remember variance, I have a whole bunch of values, could be human heights. I have a mean. If you're above average, that difference is positive. If you're below average, that difference is negative. If I add up all the differences, they would add up to 0, by the way, because I have pluses and minuses. So we don't add up the differences, we add up the square of the differences. Oh, that's what, and then we take the average of that square distance. That's what variance is, the average square distance. Then its square root is the standard deviation. That's day one practically, that's our formula. But the point being, variance is positive. Variance can't be negative because I'm always squaring everything. So I have a machine that, let's say we bottle, it's a bottling machine. You know, we fill up bottles or nasty cans of energy drinks. You know, we fill them up and they're supposed to be, Salvador, what does it say on there for the size? 12 ounces? What does it say on there?
16 ounces.
That's 16 ounces? That's not a pint. I know a pint. I know what a pint is. That's definitely not a pint. That was 16 ounces on it? Okay, 16 fluid ounces. All right. Well, I don't buy pints in cans, so let's put it that way. So he's got 16 fluid ounces. In a perfect world, I'm making these things, I'm filling them. Is every one of them, down to the subelectronic particle, is every one of them going to be exactly 16 ounces if they're being filled by a machine? Probably lots of machines, probably not. What we are assuming is that the average is probably 16 ounces, but might one can be a little bit more and one can be a little bit less? Is that possible?
Yeah.
Now, you guys wouldn't know this, but you probably know some disreputable snipes who would, you know, you hear stories about people going maybe south of the border and buying 6 packs of beverages, usually named after the sun or something, and then looking at the bottles and noticing there are 6 bottles, but the heights are completely different on all 6. Does anybody know what I'm talking about?
Yeah.
Or you've heard stories, said stories. I've witnessed this myself, but from a statistical research standpoint, purchasing, you know, 6 bottles at a time, usually named after some version of the sun, you know. Anything come to mind? Well, yeah, it could be that, yeah. And you're looking at the heights of the bottles. And by the way, I would say every human being I've ever met said the same thing. Yeah, there's not one that's the exact same height. They're all different. You probably pay more attention. But no, not radically different, just none the same. But the average will be what it says. The average will be 12. But the problem is if you get too much or too little, that's a problem. That means there's a lack of consistency. Variance basically is a mathematical measure of the consistency. In a perfect world, wouldn't they all be the same? In a perfect situation, variance is 0. That's the perfect variance. That everything's exactly the same. And I'm talking about I'm producing products. So I'm, you know, IKEA furniture and I'm making a whole bunch of things and the, you know, things fit together perfectly. Is it occasionally possible that things don't fit?
Yes.
Yeah, occasionally. That means there was just a little bit off. You can have a little bit of error and you'd be okay, but there's a point when it doesn't fit. And then you take it back and say, this one's defective or something of the like. Anytime you get something that's defective, you'd say that means it wasn't what it was supposed to be. You go in and let's say that, does anyone here go to the same place all the time? It could be a fast food restaurant. It could be, you know, a Starbucks kind of place. Does anybody go to a place all the time? What place? Starbucks. Do you get the same thing every time?
Every time.
And is it basically exactly the same every time?
No, it's slightly different.
Now, that's not a good thing, is it? But most people tell me, no, when I do that, it's exactly the same every time. No, whether it's a good or a lousy or mediocre or an okay, the exactly the same time is actually more important, believe it or not, than the quality of the thing. Because the quality of the thing, they've already determined, okay, here's how much, because it's cost too. You bought that thing might not be terribly expensive, but we'd like to make it exactly the same every time you come in.
Like McDonald's fries.
Yeah, you want consistency. Believe it or not, with companies, consistency is more important than quality. Because if quality varies, oh, I had a good experience, and then the next time I had a bad experience. I have a couple of simple rules in my life. It's really funny. I've never had 2 bad meals at a restaurant in my entire life. Because I don't go back. And if I had a bad meal and they fixed it, I don't count that against them. I've never been turned, I had never been turned down for a date twice. There's certain things I just don't subject myself to. Fortunately, my wife said yes the first time I asked her out. Otherwise, who knows? You know, history would have been horrifically altered. But the point being, like you said, McDonald's fries. Okay, they have a reputation of being consistent. Whether you like them or not, it's irrelevant.
Yeah.
It's the consistency. I've heard people tell me I went to a foreign country and I walk into a McDonald's, they didn't even speak English. And it's exactly the same. Now, that would make a McDonald's executive very proud. Now, they didn't say it was good or bad. They just said it was the same. Sameness means it's consistent. And you have to understand consistency is actually the most important objective. Quality, you've already decided ahead of time. So Jesus, you open up a restaurant, you want to be high end burger. Okay, are there places like that around the high-end burger joints? You're going to spend a little more for that burger, but you know it's going to be off the charts good. So you've already decided, I'm going to make it more expensive because I want it to be quality. I'm going to use best ingredients. I'm going to do all of those things. Okay, great. You've established yourself as it's going to be expensive, but people walk in and say, wow, that was the best burger ever. Great. But first person loved it. The next one said, oh, it's kind of mediocre. The next one, that was pretty good. And then you're finding your burgers are kind of all over the place. You created an environment where they were expensive in quality, but depending on who the cook was or who were preparing it, you've got burgers all over the map. That's terrible. That's the worst thing that could possibly happen. Because why? Somebody send it back. Mine wasn't done enough, or mine was overcooked. You go to a restaurant and you send the food back. That's the worst thing that could possibly happen to that restaurant. And by the way, by law, if that's non-negotiable, by law, they have to replace it and make it right. The fine they would pay is exorbitant. No, they don't have the opportunity to refuse that. That's an absolute law. If you go and buy stuff, now I always have fun with this because I do this in my calculus classes. I show them. Okay, you go and buy that bag of chips. And it says on 14.6 ounces, and then you open up the chips and you go, hello, 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 hello. And there's a lot of air. And it says on the bag, some settling may occur. That means that's probably a really old bag. But the point is, if that bag does not have 14.6 ounces of chips, that's what, by the way, the reason I'm saying that is because that's the common number. I don't know why 14.6, but 14.6 ounces. So you decided to pour out the chips and weigh them at home yourself, and you're like, yeah, it was 14.6. Or maybe it was 15, maybe it was 13.8. If the bag is short of what it says, by law, the company has to replace it. That there isn't, again, non-negotiable. There's a branch of the government called the Department of Weights and Measures.
Oh, wow.
That their whole existence is to make sure people are getting what they paid for. And if you complain, gas stations are the most notorious, by the way, of getting busted. You're filling up, I've had this happen more than once in my life. I'm filling up my tank and it keeps going. And I have a 13-gallon tank and I'm putting 15 gallons of gas in there. Anybody ever have that happen? And I immediately report that station. That station is making millions, if not 10 millions of dollars extra every month. It's called skimming. It's as bad a felony it can be committed by a company.
When what happens again?
You're filling up your 13-gallon tank.
Okay.
And you've got 15 gallons. It's still going. That means that they altered the pump. So you're not getting a full gallon when it says a gallon, but they're getting the full dollar amount.
That's not like some type of scam.
I'm saying that is the worst thing they can do. And I will call and report them. What I'm talking, so in other words, it's the measure of consistency. If you're going to the gas pump and you know your own car, you know when it gets to a certain level about how much gas, and then you put that much gas in and you're probably not going to be off by very much. When it's off by a significant amount, you get a little bit suspicious. Agreed? So again, the idea here is that it's a consistency thing. So let's go back to the whole point of why consistency is so huge. So that bag of chips, if I'm shorting you by law, I have to replace it. But if it's over, that means I'm giving it away for free. Both are bad. Having too much means I'm giving it away for free. Having too little means I lose more money because now I have to replace it by law. I want to get it right on the first time. I want to get it right because it costs too much money if I get it wrong. So that's what I was talking about, like the bottling plant. If there's a lack of consistency, when it's short, I have to replace it if you call me on it. And if it's too much, again, I'm giving it away. But either way, I'm losing because of the lack of consistency. That's why it's so important when I have any type of machinery that I have this consistency. Okay, does everybody understand? That's part of the reason. It's a money thing. So that's why I said companies are far more concerned with consistency than quality, because it's not that they're not concerned that I'm going to sell garbage. No, they've set the standard for quality before they started.
They explain that in the movie, what's it called? The Founder? Oh, I love McDonald's. The story of McDonald's. Have you seen it?
Oh, no, I haven't. Yeah, so, you want to start a fast food restaurant, you want to make the food cheap and affordable. It's automatic that it's not going to be high quality because you can't sell high quality food for cheap. So you're not going to have high standards, but it's going to be inexpensive and consistent, and the customers know that. They know that going in, but that's not an issue because I'm buying that cheap burger, I'm buying that cheap food. It's probably not going to be great. There's a reason I don't eat fast food. I haven't eaten fast food since I was a child. I will skip meals. I won't eat for days at a time if that's my only choice. There's two things I won't put in my body. I won't put fast food. I won't put soda. My entire life. Yeah,
And your family goes out.
Well, my family doesn't go out, but my wife will swing by the occasional time because there's one particular one that my kids love. I won't mention, but you can get in and out really quickly, I guess.
When I was a chef at a hospital, I used to get in trouble because I'm supposed to follow a standardized recipe. And I would get in trouble by the head chef because this needs
You'd make it better.
This needs it's better like that. And I would always, Ross, you have to follow the recipe.
No, I got you.
Because the consistency, they wanted
Yes.
that pork loin
Because-
exact same.
Because the next cook was going to do it differently. And
Yep.
people said, well, last night it was so much better than the
I
night.
used to get in trouble with that.
So
It happened for the
we,
patients, but
I want to make what we're doing a little bit on the relevant
True.
side, so you
I
understand why do we even care? Because again, in real life, quality control is important. You don't want garbage, but you own the company. You've decided. A restaurant's an easy one to use because if I want high end, it's going to be expensive for me, so I'm going to charge more money. But when you go out to a restaurant and you go to a high end restaurant, you know you're going to spend money, but you can't wait to go because you know it's going to be good. Am I right?
Mhm.
So you went to the high end restaurant and you were disappointed. That would be the worst. You're not going to the low end cheap place. I'm not going to trash any places, but there's cheap places, when I was growing up, they called them greasy spoons. Truck stops. I mean, truckers would stop there and get a lot of food for really cheap and move on. But it wasn't going to be high quality. You don't go there and say, wow, that was incredible. Wow, that was greasy. But it was a lot of food. But it's the consistency
Mhm.
that every time you go, you would like to know whatever it is you're buying. And by the way, it doesn't have to be food. So if we're measuring consistency, how do you mathematically measure consistency? That's what variance is. It is a numerical value that tells you the consistency of the thing. What's better, low or high variance? Low. Perfect would be 0. It's really not possible in any conceivable scenario to get 0, but that would always be your goal. No matter what it is, I make things. My brother owns a company, so he doesn't buy cars, he leases them. And he just got a brand new truck, I don't know, a month or two ago. And that truck has been in the shop almost since the day he got it. I'm not sure, just big ass truck, work truck, he owns the company. Point being, he got that truck and it was only a matter of days before it started having trouble. So he told me, he goes, I have to do the whole lemon law thing, but the company he's leasing it from is balking, saying, no, we can fix it. They've had it for 5 weeks now. He didn't have it for 5 weeks. That company who makes these trucks, it's a high-end truck. You would hope every single one of these trucks is quality because it's really expensive and top of the line everything. This is a lemon. Okay, so when you're measuring consistency, this is the kind of thing will throw you off. That's why they want to replace that. They should have wanted to replace that truck immediately, right? So they have the reputation of still everything being these great things.
True.
But when you buy something and it fails prematurely, and we talk about that, that's what a warranty is for. If things were consistent, would you need warranties? No. Again, a warranty exists for something that fails prematurely. That's the whole point of it, is to protect you for premature, I guess, wearing out would be, and again, we're always saying not because you abused it, but because it just was not what it should have been. Okay, we'll leave it at that. Yeah, definitely.
Places like Costco, they don't replace anything.
Yeah, because they want you back. Their profit margin is so slim. I was amazed one time. I had a student who had retired. He was a manager of Costco. He actually wanted to go in and become a sports agent. This is a long time ago, but he was a manager at Costco and he told me how much money they pulled in per year at his particular store. It was unbelievable, but he said their profit margin is tiny. It's way smaller than most businesses. I said, then how in the world can you survive with that small of a profit margin? He goes, quantity. They sell so much that the amount of profit is staggering, but the percentage is microscopic. My brother runs a company, so automatically you have to add 20% to everything, or you don't make any money because you have other costs and you got employees to pay. It says there's an automatic markup. But Costco was in the single-digit percentages. I mean, like really small, like only a few percent. And the fact that they take things back without question, but if they take things back without question, you're going to go back and spend more money later. They're always going to get it back in the long run. It's smart business, and it's very ethical business. But if you're saying, but I want to make the most money, I need to charge more money and I need to be a little bit stricter on my take back policy. You'd make more money, but you would only make more money per sale because you're going to lose customers. See, that's the tricky part. There's a business model that they follow. They're very intelligent about it. So what we want to do today is calculate basically confidence intervals for variance and standard deviation, because here would be the big picture. Okay, I have that bottling plant. So I make things, and I need to know, do I need to replace my machinery for any company that makes things? And I'm not talking about a chef at the restaurant. I'm talking about like mass produced things. Your biggest nightmare would be having to replace your machinery, because that would be the biggest expense you possibly could have. I don't want to replace my machinery, but if my machinery is old and outdated and the consistency of my products is just, it varies too greatly, then I have a problem, don't I? Does everybody follow that? So how would I know? Well, I have to do sampling. And then I would find a confidence interval. And I say, as long as my standard deviation is no greater than a certain amount, as long as it's in this range, I'm okay. But if it's too big, I'd say, you know what? That means I'm getting a lot of things returned. And I'm so let's use Costco as an example. You took something back because it wasn't good. We do this. I mean, my wife goes to Costco every week and we spend a mortgage payment at Costco. It feels like every week. We spend a lot of money there. And so things get taken back occasionally. But there have been times we bought something and it was just awful. And my wife took it back and she said, you need to know that this was terrible. Because we don't complain, but this thing was terrible. And every now and then they'll say, yeah, we're getting a lot of those. And then the next time she went, that thing was no longer on the shelf. They stopped selling that thing and it'll never come back, because the very fact that a lot of people were returning that thing, that costs them money. And there's something inferior about that product. And it's very likely never to come back. That's a bummer. Boy, because if you can work your way into Costco, you've done well, but you don't want to work your way out. Okay. So the concept, okay, so we know what degrees of freedom is. Okay, it's one less. My eraser. Oh, carefully hidden. So I'm going to show you how to use the table in a moment. So first of all, variance. We said, let's remind ourselves about z-scores. Z-scores look like this, where the middle is 0. And we know that the extremes generally between -3 and 3, it is unbelievably difficult in real life to be beyond 3. That's why if you look at your tables, right, you see probabilities of 0.9999, those kind of numbers. This is a Z table. A Z is how far from the mean you are, above or below, and then we can do confidence intervals easily and do the plus or minus on the error thing. This is nothing like variance. What we're going to do now is not even similar to the Z. Variance, because the smallest variance is 0, variance goes this way. Variance goes like this. This is what variance would look like, where this is 0. Now, I have not a lot of things. I have this group and I want to find out, maybe it's income. Okay, so you guys have all done your taxes, right? My oldest son, I reminded him last night, I go, have you done your taxes? No, I'll get to him. I said, tomorrow's April 15th. Tomorrow's the last day to do it without penalty. So hopefully he gets around to it today. So you've all done your taxes. And so you know how much money you made last year. So just for fun, I'm gonna have everyone write down on a piece of paper how much money we made last year, okay? And some people may not have worked, they got a 0. And I find out the variance of our group is staggering. Staggering. Why is it staggering? Oh, because last year Destiny made 3.6 million. And she bought Bitcoin at the right time, sold it, So we all made in these moderate range. And so we're doing this, but remember, variance is the sum of the square distances. It only takes one extreme value, one outlier will make the variance huge. That's why variance is open-ended. We say it's skewed. Variance can only get bigger and bigger and bigger and bigger. Oh, by the way, just so you know, Bill Gates wants to add our class. So when we do the average income for our group, it's going to look really good. But what's going to happen to our variance? It's just going to keep going in that direction. Perfect is 0. So the majority are always early, but then again, it takes one extreme value. So when we're trying to find a confidence interval around variance, there's a different number. Okay, we used Z to find confidence intervals for mu and for P. And that was actually really simple calculations, wasn't it? We calculated the error, we did a plus or minus. This is totally different. There's something called, it's a Greek X, so it's got a little tail on it. It's called chi-square. Now, this is the weird thing. The variable is this. It's not the X, it's the square. This is the variable. It's called chi-square. Chi is a Greek letter. Remember, we always use Greek letters. Chi-square is the variable that we're using. And the chi-square, unlike the Z, Z is perfectly normally distributed. We have the perfect bell-shaped curve. Chi-square looks like this. Okay. So this is a new variable, and it's only used in conjunction with variance, which is part of the reason I think it's called chi-square, to remind us, oh, sigma squared is the variance, isn't it? Now, you don't know what the population variance is. You don't know what the variance of the bag of chips are for the population, do you? But could you collect a bunch of bags of chips, measure all of them, and find the variance? Yeah, that would be, I mean, you're going to do it as a fact-finding mission, so you're going to get support from somebody else to buy it. You're not going to pay, you don't pay out your own pocket $3 or $4 a chip. Come on. So you're gonna get 100 bags of chips. I sell tires, and I'm telling you, your tires are gonna have 40,000 miles, but we find out it's all over the map. When it comes to tires, I'd rather they last longer than I advertise than less. But if my tires are really inconsistent in their quality, my variance is going to be large, which means you bought 40,000 mile tires and they burned out at 20,000 miles. That company has to either replace them or give you prorated. That's what they do. They lose money. Your tires lasted 60,000 miles. You're going to maybe buy another set from them. Great, you got 60,000 miles, but they were only supposed to get 40, so you didn't buy more tires from them for a long time. They didn't make money on you for a long time because your tires were too good. Isn't that funny? They were too good because you drive really carefully. Rosalind, if you know, just only drives 10 miles an hour and she mostly coasts, so she doesn't have to use her brakes. So for the tire company, too good could be bad because you're not buying more tires because they're lasting too long. So instead of 40,000, maybe I up them, they're 60,000 mile tires, and now I can charge you more. That's how tires usually work. But the idea is if things are all over the map, again, things have to be replaced and we lose money. Tires are a perfect example. When tires wear prematurely and you're driving safely, you're not a race car driver. You're not Vin Diesel doing the whole, street racing thing. You're driving a normal thing and your tires are wearing out way prematurely. They have to replace a prorate. That's how it is, because the tires were guaranteed to last this long.
That's how it is, so I can have lashes on, and if they start falling.
40,000 mile lashes, or?
If they start falling out faster than they're supposed to, they'll give you a fill for free, like one free fill.
Interesting. Okay, so what is the value of chi-square? Chi-square equals n-1 times s squared. S squared is our sample variance, divided by sigma squared, which is the population variance. Okay, now n-1, that's easy. That's 2 degrees of freedom. S squared, that's easy. You went out and collected a sample and you calculated the sample variance. That's easy. But you don't know what sigma squared is. How could you know it? You couldn't know what sigma squared is, could you? Oh, did you see a problem with that? If I knew sigma squared, would I collect a sample? No. But I'm gonna look up this number. So check this out. This is the value of chi-squared. What if I multiply and I divide, then wouldn't it be true that sigma squared equals n minus 1 squared? I'm sorry, n minus 1, sorry, s squared over chi-squared? Right? Multiply by sigma squared, divide by chi-squared. They just swap places. Oh, I don't know the value of this. I'm trying to come up with a confidence interval. So I'm going to look up a number in my table that I gave you. I'm going to show you now. I know that number. I know that number. I calculated it.
I'm sorry, Professor. I missed why we did it backwards.
Oh, well, we don't know the value of sigma squared. We're going to come up with a confidence interval. Last day we came up with a confidence interval around mu because we don't know the value of mu. We only have our sample mean. We had X bar. The day before we did a confidence interval around the true probability you were going to make a free throw using our p hat, our sample. So we're going to make a confidence interval using S squared, which is easy to measure. We collected a sample, we calculated S squared. So if I multiply both sides by sigma squared, it goes here, divide both sides by chi squared, they simply swap places mathematically. Now, I look up this number, I'm given this number. This is a simple calculation, so it means I'm going to give you this number too. And that will tell us, but the thing is, that's one value. Oh, what we're going to do is use two different chi-squareds. We're going to use two different values that we look up in the table so that we can get, remember the confidence interval is a range of values, but the difference is this is not a plus or minus. This is, I'm going to look up two numbers in the table, and the part of the reason it's not a plus or minus is there's no middle. Plus or minus only worked when it was a normal distribution because I have the bill. This guy here is way skewed. So I'm going to look up two chi-square numbers. So look, hypothetically, I want a 95% confidence interval. What does that mean? That means 5% in the tails. You remember that? Well, 5% in the tails means I have a little bit in this tail, and I have a little bit in this table, and I'm going to show you how to look up those numbers. Okay? And the looking up is easy. So what we're going to do is create a confidence interval that looks like this. This is totally different from what we did before. The true value of sigma squared is going to be between n minus 1 s squared over one value, n minus 1 s squared over a different value. Now, this is known. I know what that is. That's given. That's the numerator.
Which one's known? I'm sorry.
N minus 1 and s squared are known.
Or no?
We're going to know those numbers.
Okay.
We're going to look up the chi-square. So here's how it works. There's going to be two chi-square numbers we're going to look up. And I'm going to make it really mathematically formal. The big one and the small one. We're going to look up two numbers because if this denominator is big, then this quotient is small. If this denominator is small, then this quotient is big. Does that make sense? That's mathy stuff. This is how we do a confidence interval for sigma squared. Now, if I want a confidence interval for sigma, what would I do? Square root. That's easy enough. Okay, so now everybody go to your tables for a moment. If you can grab the chi-square table, does everyone have one? Okay, look across the top. It says area to the right, 995, 9997. What does that mean? Well, remember, we talked about, let me go back to my picture. Let's say hypothetically, let's start with a 95% confidence interval. Then that means I want 5% in the tails total. So that would mean I want 2.5% in each tail, just like we did with the z's. You remember that? But the chi-square is a little bit different. Chi-square says the area to the right. Okay, so that means that this would be the 025, wouldn't it? Because that's what's to the right. So if 025 is to the left, then to the right would be 975, because these got to add up to 1. And what's between 975 and 025? Exactly 0.95, which is my 95%. So let's look up a number, okay? Now I'm going to bring this up to the screen now, because I want us all to see the same thing. Well, actually, yeah, I'm gonna do it this way. If nobody was on, I would. Come on. All of my classes is doing this now. We won't lock. There we go. All right, is anything happening yet? Slowly but surely. There we go. All right. Let me do this. This is funny because it says Lila's speaker. Go back to gallery view. Full screen. There we go. Okay. Can everybody see this now? Now, Lila, this is from the, if you go to the Triola where we get the Z tables in the internet, it's pretty easy. Now, there's a lot of numbers here. Hold on a second. Hold on a second. Does that give me the right one? Oh,
No, it's
sorry.
not.
This, sorry.
I was checking them.
One off. Get off there. There we go.
That's the other side.
So this is the chi-square table. So this is exactly what you have in your hands. Yours just isn't in color. It's the same thing exactly. Oh, you have that. Oh, you have that from a previous. Awesome. That's what I just
Yeah.
Xeroxed off for you right before class. I didn't bother with color because that's more expensive. So when you're looking at this, you see all sorts of numbers everywhere. But look at the top heading. You would put these two together. You would put these two together. You would put these two together, these two together, these two together, because they have to add up to one. If I have a 95% confidence interval, that means 5% in the tails. A 90% confidence interval means 10% in the tails. 99% means 1% in the tail. But since everything's measured to the right, 995 to the right means 005 to the left. 0.5% tail on the left, 0.5% tail on the right. So that's why your columns will match perfectly. So all you have to do is go slow, make sure you're in the right column. Now, let's do an example where I'm going to give you some numbers. We measured, and let's say S squared was 23.57. Okay, doesn't matter what, we're measuring something. Let's say our sample size was 27. And let's say we want a 95% confidence interval. Then again, the idea is that you've already calculated S squared, which means I'm going to hand it to you. You guys know how to calculate S squared. That's not what we're doing here. So, or maybe you have a team of statisticians working for you. They collected the data, they calculated it for you. What numbers am I going to look up? Well, first of all, okay, if my S squared is 23.57, that's going to go in the numerator. My N is 27, so how many degrees of freedom is that? I would not use the term degrees of freedom if it was the same as N. That wouldn't really make any sense. Degrees of freedom is not equal to N ever. We spent the first 15 minutes of class going over that. Come on, what's degrees of freedom?
26.
It's N minus 1. That's degrees of freedom. That was the whole first almost half hour of class. N is 27, degrees of freedom is 26. 27 is not used anywhere in the rest of the problem. Degrees of freedom is 26, so I go to 26. So my magic numbers are going to come from that row. So look at your table, because this is too far away from you. Okay, look at your table. Now, I want a 95% confidence interval. So there's two numbers I have to look up. Okay, sorry, Lila, this is to the left of, or to the right of your screen. I need to look up the chi-square that's 0.975, that's 2.5% to the left. And I need to look up the chi-square of 0.25, that's the 2.5% to the right. And I know I did it right because these two numbers add to 1 and their difference is 0.95, which means 95% confidence interval. You get it? The two probability numbers as subscripts have to add to 1, but their difference has to be this. Oh, 975 minus 0.25 is 0.95. I know I did it right. But the easiest way to think about this is, where did 975 come from? Came from the third column from the left. Where did 025 come from? The third column from the right. Remember I said they got to match outer, outer, boom, boom, boom. So let's write down the numbers. The 975 at 26 degrees of freedom is what? 13.844. The 025 number at 26 degrees of freedom, 41.923. You don't calculate these. These are computer generated.
Okay, Professor.
Yes.
So the way that you got 20, the way that you knew 26 was the degree of freedom is you took n and you minus one.
One left.
Because okay,
One
just
left. Yeah.
making sure.
Just one. Remember, the formulas themselves have n minus one in them. But the problem, you say, oh, well, it already has n minus one in them. I'm already going to have 26 in my formula, but that's not the point. I need to know that I'm looking up 26,
Got it.
not 27. The formula that we're going to use has an n minus one in the numerator. That means I can't really get that part wrong. But if I look up 27 rather than 26, I'll be using different numbers. I mean, they'll be close, but they won't be the same numbers. So what am I going to do? Now, Lila, do you have this? Do you have the ability to bring this up at home?
Yeah, I searched it up on Google and it's there.
Okay, so if you have this on the screen, I'm going to go ahead and lift this up for a moment so we can do the calculation. Whoop. Okay. I don't want to turn that off because it takes it on long to warm up again. Well, but then it's not getting recorded. Okay, I'm going to turn it off for just a moment. I don't want to do this. Okay. It's getting recorded, but this is the formula we're going to use. We just wrote it down. So, what am I going to use for this problem? Sigma squared is between what and what? Well, n minus 1 is 26. S squared, 23.57. It's be over something.
What is that next to the n minus one on the first one?
Oh, I just erased it. Sorry, it's S squared.
Oh, okay.
Yeah, I partially erased it. The numerators are the same on these two. Sorry about that. Same numerator, different denominator. So on the left side, I'm going to have 26 times 23.57. What are those? Degrees of freedom times the sample standard deviation. Now, which one's bigger? I think that one's bigger. This is what I mean by big and small. That one's bigger, so that goes first. So 41.923. And over here, what goes here? Now, the idea is we don't know the true standard deviation of the population. In fact, that's not reasonable that we could know that because we don't have the whole population in front of us. You've decided to go on a fact-finding mission and sacrifice your own well-being to determine the consistency of French fries at McDonald's. So for the next month, you go to every McDonald's in San Diego and you buy French fries. Now, you're going to not measure the quality so much as the quantity. You get the same number. And I use that one as a very specific example because that's one I can have fun with in a moment. So you sacrifice your own health and well-being for the greater good. So you're going to have French fries every day for the next couple months. And you found that the variance was very large. Would McDonald's be happy if the variance was large on the French fry servings?
No.
No, because that's a lack of consistency. I can say this with fun. When my kids were little, they're really spread out. So there was always somebody little. So my wife would use that as an excuse. She used to like to go swing by a McDonald's and get fries, but there was only one that she would go to. Because that particular one was known for always giving significantly more fries than anywhere else she'd ever been in her whole life. At McDonald's, it was known for giving you way more fries than every other McDonald's. So of course, that made a mom very happy. Would that make McDonald's Corporation very happy? No, they'd be furious if they knew that one had the reputation for big. Well, now that sounds like goodwill, doesn't it? I mean, but also losing money. She had literally 50% more fries. You know, when you buy the fries, the whole bag would be filled with fries, the overage. You know, that's why she would always go to that one. I couldn't tell you where it was because I've never been there. So the point being, as a company, that's not good. That's a complete lack of consistency. So let's calculate these values, shall we? Calculation should be pretty easy. I mean, you just need one of these. That's, sorry, this is S squared. You're not squaring this. Everybody understand? That is S squared. If I gave you the standard deviation, then you would need to square it. Agreed? I'm giving you the variance, so that just makes it easier. So you can do as many decimals as you like, actually. So let's say we're gonna go 3 places. So what do you get for the first one? Anybody?
0.617. So 0.618.
That's, you're asking me, do you round it?
Dude, rounding is confusing.
You always round. Because you're not writing an infinite number. There's no scenario that exists in the world that you wouldn't round. Yeah, you always round, you never chop off. Yeah, chopping off would be if you chopped off the whole decimal, but you're, so 6, what? 1,
14.617. Or 8, yeah.
yeah, 8, because the next one's more than halfway.
Uh-huh.
Yeah, when people say, should I round or should I ignore? There is no situation that exists where you ever ignore. That doesn't exist. If somebody told you that, they wanted your money. They they want to sell you that beachfront property in Arizona, for the big quake that's going to come. Yeah, all rounding rules are exactly the same in all contexts. So it's never something you have to think twice about. All right, so what's the next one?
Oh. 4.27.
Well, probably should go the same number of places you did the first one.
267.
What are you looking at? 2661.
Oh, I was looking at it wrong.
Probably
Dude,
266.
I freaking hate this calculator because it's so dark and the numbers are black and the screen is.
You can,
really-
well, I'm not sure this is going to be better though. Is that any better in terms of the building?
These numbers are bolder than these ones.
I think it's because the numbers are just slightly larger.
Yeah.
Also do understand, I got some of the lights off. That might affect, the farther you are away from that is probably easier to see because up front, there's no light up front because I turned them off for this. Now, what does this mean? Let me put it here. This means with 95% confidence, the true variance is between these two numbers. That's a pretty wide range. But now if I wanted the standard deviation, can you give me a confidence interval for the standard deviation? Can you? Yes. What would you do? If the standard deviation is the square root of variance, then how would I give you a confidence interval for standard deviation? Let's say, okay, a new problem, brand new question. I want that. That's it. You take the square root because that's how you get standard deviation is by taking the square root of variance. So when I talked about finding confidence intervals for variance or standard deviation, because it's the same mathematics, sigma squared is between these two numbers. So sigma is between the square roots of these two numbers. Oh, okay. That's a fairly simple thing, isn't it? So I've got a company and I say, you know what? I want consistency. I want consistency. You're never going to have variance of 0. That's really not realistic. I'm trying, I can't really think of a situation where your variance is 0, but think of things that you purchase. Tennis balls, perfect example. Anybody ever play tennis? My boys have taken up to it recently, so we've been buying a lot of tennis balls. And you open up the can of tennis balls, they look the same, they feel the same, they usually have the same level of non-squishiness, hopefully, when they're new. But every now and then, I played tennis all growing up. I'd buy a can and I can squeeze these ones. That's bad. Because that means it's already going to be poor. It's already not going to bounce. So you were going to buy tennis balls. You want them all bouncy. You want them all to last a little while. Now, has anyone here ever played a lot of tennis when you're growing up? Man, you hit a tennis ball for a while. It's going to wear out. But you go, you know what? I probably get a week out of that tennis ball. But there'd be tennis balls that maybe lasted you 2 or 3 weeks of regular playing, and the other tennis balls lasted you a day or two, and they're already getting soft. And you'd say, you know what, these are not well made. And then you start looking at brands and go, you know, this brand seems to last longer than this brand. And that's definitely true. And that brand that lasts longer is probably a little more expensive. And then you're watching Wimbledon and you wonder, what balls are they using? Oh, they're using that brand, good. But if you ever watch tennis on TV, anybody? Oh, Roger Federer, Rafael Nadal, Djokovic, those are the greatest, you know. And what do you notice when they're playing? How long do they play with that ball? A few points and then they switch out. They're constantly switching out. They literally in a tennis match, they might go through 50 to 100 balls because they're constantly keeping them new balls. Oh, isn't that interesting? Because they don't want that ball to get lifeless and squishy. But the consistency of, for the player's point of view, they want every ball to feel exactly the same. So if you're a tennis player, you don't want one ball to feel different than the other ball. Okay. So Robert's a football player. Your quarterback is used to throwing a football. Would you say it's safe to say your quarterback wants every football he throws to feel exactly the same? The feeling of the ball, the weight of the ball, the inflatedness of the ball. Because if it's different, it's going to feel different. The ball is going to travel different. Except, no, well, do you guys remember Deflategate? It's a classic NFL scandal where the Patriots, they were supplying the footballs and the Colts footballs were different than the Patriots footballs. Why? Because it was really, really cold weather, and in really cold weather, a perfectly inflated ball is harder to throw and hold on to because it's slippery and hard. So the Patriots footballs were all slightly deflated because then it was easier to hold them to throw. That's why it was called Deflategate. That's a classic name, and they didn't need to cheat to win, but you know they kind of had a reputation at that point. But the thing was, is every single football in a football game, in an NFL game, every football should feel exactly the same. And they do rotate footballs. They don't constantly use the same ball for the obvious reasons. If you're playing in weather, it's raining. Why do they rotate footballs constantly? Because once a ball gets wet, it's really hard to throw. So they'll rotate maybe even every play and be drying them off and putting them in front of heaters on the sideline so that the quarterback has a dry football. If you're handling a wet football, right, Junior, you're running back and they give you a wet football, what's a potential problem? Fumbling because it's slippery. So football's a perfect example. You want consistency. You want the ball, regardless of the players, you want the ball to be the same. Anybody watch baseball? How many baseballs do they go through in a game? Yeah, many. Let's just say many. Foul balls, or pitcher throws it and they throw it out. Sometimes the umpire will throw the ball out because it looks like it might have been stuffed or something. Oh yeah, that too. That's real cheating. But even in baseball, they want the consistency. Now, here's an interesting thing that baseballs themselves, you think of all are exactly the same. Actually, they are not. Baseballs that come from wherever that baseball was produced are probably pretty much the same, but they're produced in maybe multiple places around the world. Oh, so the standard from one place to the next may not be identical. So baseball, whatever governing body, they are constantly testing the balls. Ah, okay. Yeah, they use terms like juicing the balls. Some baseballs may travel farther because they're wound tighter and things, but that would not be good, would it? You want a consistency. Basketball. Would you want, in a basketball game, would you want your basketballs to be different diameters, even if it was just slight? No, because it would feel different when you're shooting the ball or dribbling the ball. You would want basketballs to be identical across the board for every single NBA game, heck, every high school game. So again, when we talk about consistency, when it comes to something like that, we've talked about the balls used in different sports, tennis balls, footballs, basketballs, baseballs. Even soccer, wouldn't you want your variance to be as close to zero as possible? Is it possible, because human beings are producing these things, to get a variance of zero? Is it possible? No, but can you have variance that's very small if you really, really are strict with your standards? Yes, you can. Now, how do you know when it's too much? Well, you do tests. When your sample standard deviation or sample variance is too big, then you'll see evidence your range of values is just too big. Maybe this is acceptable, but this is unacceptable. And so you'd want that cushion in a sense. This is not a plus or minus, is it? My sample variance was 23. Isn't my sample variance closer to this number than it is to this number? That's usually the way it is. Remember I said it's skewed? Your sample variance is always going to be closer to the smaller number than it is to the bigger number, because the bigger number can keep going forever and ever and ever. So let's do another example, shall we? So this time what we want to do, let's construct, that's always the term we use, a 99% confidence, let me spell it correctly, confidence interval for sigma this time, not sigma squared. We'll do it for sigma. That's not more work.
Correct me if I'm wrong, but isn't it at 0.0251?
Well, now we're going to be using different ones. This was the 95%. So I want to vary it up so you know, so you get used to looking at the right place. Okay, and so here's what you have. I'm going to give you an n. Make simple. I'm going to give you an n of 81. S squared was 42.96. It was, these are really big numbers we were using. That's all you need to be given. Sample size and the sample variance. Now, if I gave you the, by the way, and I do this on the quizzes, I'm going to give you the sample mean also, just for fun. Just for fun, let's suppose I gave you, and the sample mean was 396.8. I could be measuring tires. I could be measuring, there's a million things I could be measuring. If I wanted a confidence interval for mu, I would use this number, correct? If I wanted a confidence interval for sigma, I would use this number. So you're often given all the numbers because you're often asked for all the confidence intervals. So just so you know, the quiz let's see, which one did you turn it to?
16.
Yeah, but you did the confidence interval for P today. On Thursday of next week, you're going to turn in the confidence interval for mu. On the following class, you're going to turn in the confidence interval for sigma. But in the mu and sigma case, you're usually given both X bar and S squared. Just make sure which one am I finding the confidence interval for? Because you have the same information, but you're asked for something different. So what I did, just to make it easier on you, I gave you the exact same quizzes, 2 quizzes in a row. Quizzes 17 and 18, did you look at them?
Yeah.
Exactly the same numbers. I gave the exact same numbers, but I asked you for confidence intervals for mu on one of them, for sigma on the other, starting with the same values. So that's, oh, which one am I finding? Does that,
Oh, I see.
that's, and your answers are different because you're using different things, but it's the same big situation. So I have a company, this is what we have. So what am I using for this problem? I'm only using this number, and I'm looking up my chi-squares. Now, what chi-squares am I looking up? It's a 99% confidence interval. So that means 5.05, right? 005 in the tails. So that means I need to look up 995 and I need to look up 005. Quick check, they add to 1 and their difference is 99%. That's why I know it's a 99% confidence interval. So on my chart, they are the furthest columns out, aren't they? It's the first column and the last column. 995 is the first column, 005. If you don't get anything else, you're always matching columns. The last or the next or the next, they go in pairs. Okay? So what is the degrees of freedom in this case? No, degrees of freedom. 80.
Oh.
I had a question.
Oh, yes.
So for, on the chart for degrees of freedom on the top, if it was 0.99 and 0.01, would that be a confidence interval for what percent?
Well, what's the difference between 0.99 and 0.01? 0.98. So that'd be a 98% confidence interval, wouldn't it?
Oh.
Because you'd have 1%.
I get it.
Does that make sense? Everybody understands it's a great question. Salvador said, okay, let's go to the second column in and on each side. So you have the 0.99 to the right and you have 0.01 to the right. That means if you have 0.99 to the right, don't you have 0.01 to its left? Because
Oh, okay.
so the difference between
I
those,
see.
the difference between 0.99 and 0.01 is 0.98. That would mean it's a 98% confidence interval.
So for 0.95 and 0.05 would be a 90%.
Beautiful. And it just keeps working that way. So we're in the very last, we're in the extremes. 995 and 005, the difference is 0.99. That's why it's 99%. And they add up to 1 to make sure that, okay, that worked. So all I got to do is write down the correct numbers. So 80 degrees of freedom. Everybody agree? I'm gonna write DF equals 80, because that's where I'm looking. I'm looking at the row where it's 80. So everybody, what is the chi-square value for 0.995? 51.172. What is the chi-square for 005?
116.
Yeah, just look at the other end of the table.
I don't know where we're looking.
Okay, find your row, 80 degrees of freedom.
Okay.
Okay.
So I just have.
And this column.
The outermost column.
Oh, okay. Got it.
Remember, you're not calculating, you're just looking them up.
Okay, got it.
But today is all about where do I find it? What's the right one to look up? There's no calculation involved. I just got to look at the right one. Now that we have the numbers, can we create a confidence interval? Yes. So I'm going to write, I'll do that above. I got room. Okay. So I take my n, I take my s squared, I take the bigger number, so I take that one, 116.321. And then over here, same numerator. This part is great. You don't have to change your numerator. I got that. But the other chi-square number. Now, this is the confidence interval for sigma squared. But I said I want the confidence interval for sigma. So what should we do? I want it to be sigma. So we're just going to go like this. That's it. Is that easy enough?
And that's if you want sigma squared.
Well, now I wanted sigma.
Okay.
Sigma squared has no square roots. Oh,
So
but how do you
sigma
get?
was before you get the square root on here.
Yeah, well, before the square root, it was sigma squared, but I want sigma.
Okay,
So think about just square root.
okay.
That's not extra work. Now, the nice thing is there's no adding or subtracting. It's the square root of the whole thing. This is where you want to use parentheses. Square root, parentheses, this times this divided by this, close parentheses. Because if you don't do it that way, then all the numbers won't end up under the root. I need all the numbers to end up inside the root. So let's all try this and see if we get the same numbers. Tell me when you have a number for the first one. And probably 2 choices for the standard deviation. That's kind of what we've been doing. Robert, do you have a number?
5.496.
Close.
Oh, 5.47.
Wait, it's 5.469. You had those back. Yeah.
Oh, I guess I'm
So to 2 places, 5.4.
69.
To 2 places, 5.4. 7. Okay. You keep changing on me here. So Robert says the first number is 5.47. Does everyone else get that?
Did I?
And this one got your pencil.
Okay. Did I use?
Yep, perfect. Now just hit equals.
Oh,
Enter.
that's it?
Yeah.
Oh, okay.
By the way, I love that your calculator showed you it as a whole picture, because you're saying, when you're doing stuff like that, don't write this down, by the way. When you're doing stuff like that, a lot of people make the mistake of what they actually entered. What they actually entered may be this. Well, is that different? Yeah, this is not in the root. It's going to be a very, very different answer. Oh, so your calculator, when you looked at it, you saw all of it was inside the root,
Mhm.
then you can trust it. Okay, I'm gonna get the right number. You know, and it's not hard to enter, but you need to use your arrow keys sometimes to move yourself around. Yes.
When would you subtract one from n?
When would you subtract one from? Did I? Oh, you know what? Oh, thank you, Salvador. No, he's right. You have the wrong number. Good catch. That's gotta be at least 100 miles you get. I'm gonna add 100 miles to his account. I did not do that intentionally. That should be what? 80. Oh. And if you guys knew that and didn't speak up, why didn't you speak up? That's supposed to be 80.
We were trusting you, Professor.
I'm the only one that's not gonna see the mistake. When you're at the front, you have tunnel vision. Yeah, good catch. That's supposed to be 80 because that's my n-1. That's my degrees of freedom. So let's recalculate that. It won't be the same. It won't be very different, but it won't be the same. It's gonna be a little bit smaller.
That's extra credit right there.
Well, it's airline miles. That's because you guys know I give out airline miles. I had somebody text or email me last night and had a question and they said, don't forget, you know, I have another 200 miles on my account or something. They actually keep tracking my calculus classes. Because I dole out airline miles for good work and, you know, good.
What's
Oh,
Errol? What is it?
really?
Yeah, now they have no cash value and they're not redeemable, but everybody feels better when they get lots of miles, don't they? So a lot of people say, I've already earned 1,000 miles in that course. So that's, by the way, rarely do people earn 1,000 miles in my course, but I have a couple that claim they have so far this semester because I don't really keep track myself, but.
So 5.43.
Sure. 5.435, so 5.44, good. Yeah, we can't ignore, now, by the way, if you said 5.43, will that be earth shattering, life changing? It will cause my company to go down? Probably not.
No.
But we do want to round correctly, you know, it's a good thing to do. All right, how about the second number? So square root, by the way, same numerator, that didn't change. Does anybody have a second one yet? 8.20, good. And I put the 20 because that shows that I did round to two places. Now, that is not a huge range, is it? Now, your company might say, I can live with a standard deviation, whatever it is. I can live with a standard deviation of 6 and 7, but maybe 8 is too much for whatever we're doing. Or you're saying, you know what? For my company, as long as my standard deviation, whatever it is, as long as my standard deviation is less than 10, I can live with that. And I'm saying 99% confidence I'm between here and here, you would be happy, wouldn't you? Because you know what? It would almost be virtually impossible to be outside of this range. So therefore, I don't need to replace my machinery. I don't need to spend a lot of money. Okay. Now, has anyone here ever worked in the service industry? I know you said you worked at a hospital. You've been trained and now you've been there. You make mistakes when you start. So now you've been trained. You do things. What if you were all over the map on your thing, or let's just say something like as simple as your on time record was all over the map, like you're late constantly, or you know sometimes you don't even show things like that. Will that be held against you? Yeah. What if you're always a few minutes early? Is that a good thing?
I'm always.
Because that means you're always on time, you're never late. Does anybody care if you're an hour early versus a minute early? No, you're early, you're not late. That's usually kind of what it comes down to. But whatever it is you do, has anyone here ever been a cook? You've been a cook. Okay. As a cook, what is the worst thing?
I'll wash your hands.
No.
Oh, sure.
No, yeah, that's bad. Okay, I don't mean that. You're a cook. You make things. You have customers. What's gonna? Yeah, I'm assuming you're all washing your hands. Okay, I'm not talking about that. You're a cook. What is the worst thing? You're a cook. What would ruin your day as a cook? Yeah, no, not washing your hands might ruin someone else's day. What's ruining your day as a cook? You probably just made this great meal, great steak. Somebody complains. Somebody sends the food back.
Yeah.
Oh boy, does that make you feel good when they send the food back? No, you're mad at them, aren't you?
Yeah.
No, you said I messed this up.
Some people send their food back because they don't read the menu to see what's on it.
That's, okay, so you got your food sent back, it wasn't good, okay. You're a cook. Now, how do we measure the consistency of a cook? Because the manager is not taking a bite of everything you make. They'd be really big if they were. So what is one way a manager can measure your consistency? No, because you're cooking the food. They're giving you the order.
How many people send it back?
Yeah, or how often do people send it back? Oh, so you're just cranking out things all day long. You're a short order cook. I've known short order cooks. That is high pressure. I mean, because speed, it's not just quality, but speed. You're making it perfectly, but it's taking you too long. So the customers are complaining about how long it takes. So you're a short order cook, and so maybe you made 100 meals today, and 10% of them got sent back. Good, bad. Probably fired.
Yeah, that's it.
Why? Because that means that 10% of the orders they had to remake, which means they lost all of that money, which means basically they didn't make any money today. They broke even because you messed up 10% of the orders. Oh, could they live with one order being sent back? Yeah, probably. How about if nothing got sent back? Oh, your picture's on the wall, right? Employee of the month kind of thing. So how would you measure the consistency of the short order cook? By the frequency, or how often does the food get sent back? Because what else? You can't say, you go up to Rosalind who bought food and say, Rosalind, what do you think about your meal? Oh, it's fine. Really, it's what we're hoping you're saying is it wasn't bad. If it was really good, that's even better. But mostly we're hoping you didn't dislike it. Because if you disliked it, it's a knock on him as a cook, but it's a knock on us as a restaurant.
Yeah.
And bottom line is we're losing money because we have to replace that thing. Ooh. So when we're talking, again, I said at the beginning, it's not the quality that's the most important, it's the consistency, because you've already decided the quality ahead of time. Again, when Junior opens up his super burger chain, by the way, his burgers are gonna be like $30. But it's like the best grass-fed meat. These are cows that they had people playing violins to, and just really happy cows, right? And just everything is like off the charts good. Well, that means that you're expecting every customer who leaves that is absolutely satisfied, want to tell their friends. Has anybody here been to the movies in the last 3 or 4 years? Let's go pre-pandemic. Your usual cracker box movie theater. My son was telling me they need to redesign all movie theaters in the US. They're still using designs from the 40s and 50s. But a few years ago, I don't know how many years ago, but it's been probably the early 2000s it started. You could go to a movie theater and you could order a drink or order some food, and you sitting in a chair that reclines. Have you guys ever been to one of those?
No.
Oh my gosh, you go to the theater, you're sitting next to your spouse and you're sitting in the recliner, try not to fall asleep, totally comfortable, and there's nobody right next to you, and you maybe have whatever it is you wanted to order from the bar or something, like, this is a movie theater? I feel like I'm at home with a big screen. This started happening, and at first it did not catch on because it was just too expensive. And then when people started, okay, this will be date night, this will be a big deal, and then they went and realized, I don't mind spending a few extra dollars. This is infinitely better than sitting in the crowded theater with the screaming kid who chose to sit right behind you. Or the last, I can't remember what movie I went to, but it was a biggie. It was probably like Endgame or something. And the kid behind me is yelling out what's about to happen next for 2.5 hours. And I finally had to threaten father to shut the kid. I'm going to death. And that, in fact, that he wouldn't stop kicking me every 8 seconds. Yeah, and the father's like, well, he's got Tourette's. I said, Tourette's doesn't cause you to kick people. It causes you to speak out of turn. No, it was a parent who just said, anyway, so I will infinitely take the theater with the reclining seat, and I will pay more. Now, you did that and you didn't have a good experience. You've done it a few times. Your friends have done it and they did not have great experiences. Will that last very long if that were the case? No, because the idea was to make this high end that everybody leaves very happy. It's not about the money, because you already knew you were going to spend money.
Yes.
It was about, did I enjoy my experience?
That's right.
My favorite restaurant, well, actually my wife's favorite restaurant, we love going up to Stone up in Escondido, the brewery. Love Stone. But when we go to Stone, we're going to spend some money. It's a half-hour drive. We know we're going to spend money. In fact, we spend a lot more money because my wife loves going to the gift shop and buying shirts. We have so many Stone shirts. She loves going to, but we have 99% of the time, we have an incredible time, a fantastic meal, and so relaxed, and there's no rush. You can take time, you walk around. We know we're going to spend money. We don't, it doesn't matter. We know we're going to spend money. We only go maybe 3-4 times a year. You know, like her birthday, anniversaries.
I've gone 6 times in the last 2 months.
Wow. But the point is, I already know I'm going to spend money. So that's not part of the equation. It's the consistency, because the last time I went, it was fantastic. If this time it's not fantastic, then I might think twice about next time. So all they care about is the consistency of the performance of what they do.
Yeah.
They've set the bar extremely high. That's why it's expensive. Has anybody ever been, Ruth's Chris? Anybody ever been there? I was there once. My brother gave me a gift card for my birthday. He was like $200. And that was almost enough for my wife and I. You know, the $50 potato. Now, Ruth Chris, it was unbelievably, incredibly great food. But that's not a place you go on a regular basis because the price is so ridiculous. You know, the salt shaker, you rent it, you know, it's like $10 a shaker. No, everything is, it's the most expensive thing you could even imagine, which is why I would never go there, but I was given a gift card. So that's why I went. It was incredible. But every person who walks in there is expecting unbelievable off the charts. And if it's anything less than that, that person's never going back because not for that price. But if you were a person of means, if money was not even a thing, you were wealthy, you're still not going to go back if it's not incredible, because you can spend a lot of money at a lot of places. There are a lot of places that are very expensive. Why would I go to that one if it doesn't blow me out of the water? Again, what are we measuring? Consistency. We've set the bar up here, but now we want it to stay here. If you're going to, okay, I'll say it. You're going to Denny's for lunch. You're going to Denny's for breakfast. You're going there because it's really cheap, it's really fast, really convenient. Are you expecting off the charts?
No.
No, because you're not paying for off the charts. But you would like to know that it's the same as the last time and the time before the time before. You don't want to have a bad meal. You already know it's not going to be off the charts because it's cheap. If it's cheap, it means the quality of the food can't be off the charts because otherwise they'd have to charge you more money. So again, it's not about the quality that's decided ahead of time. It's about the consistency. That's what variance is, period. Now that we understand that, let me bring up the problems on today's stuff. Does that, you guys kind of get a clue of what the whole point is?
I had a question. You were gonna bring up the quiz, right?
Yes.
So on the quiz, it says S, but not squared.
So that means I gave you what? The standard deviation.
Yeah.
So what are you gonna do? You're gonna square it.
Okay.
Yeah, this, I gotta vary it up a little bit so you realize, oh, if I'm asking for sigma squared and I give you sigma, if I'm asking you for sigma and I give you sigma squared, if I ask you, yeah, there's but there's just a squared relationship. So that makes it easier.
Yeah.
In the end, you're gonna use a calculator for everything anyway. Aren't you glad you don't have to do this by hand? Do you know that statistics was literally invented in the early 20th century? And there hasn't been a lot of great advances. Statistics is only a little over 100-year-old field. But how did they do this problem? I have no idea. There were calculators didn't exist. But by hand? I mean, how do you do the calculations? Think about that. They had knowledge, but how even 30, 40 years ago, I mean, calculators were, you know, not commonplace yet. Wow. So yeah, oh, sorry. No. Gotta get this on again. Now, a reminder, this is quiz 18. Yeah. As a reminder, tomorrow we'll be doing our Zoom review.
What time? What time? It was 12:15.
Didn't we decide 11 to 1 last time? Did somebody had a problem with that, but I think O'Shea, you had a problem with that, didn't you? You had a problem with that?
Matter to me.
Because when I asked you guys, I got unanimous. It doesn't matter to me. I'm doing it from home.
No, I am too.
I think we should change it.
How many would prefer 12 to 2? Given the choice of the 2 times. How many prefer 11 to 1? How many don't care? See, I'm a don't care, but I want to go, is there anybody who one time actually excludes you? It doesn't have to be, but I want to sleep in, or I want to, no. Is there anybody that one of those times actually means you can't go? Which one?
11 and 2, or 11 and
What's happening at 11
outward.
until? Well, then you wouldn't be able, wait, what time do you go? Well, then you won't be able to go anytime.
Right.
So 11 to 1 or 12 to 2 doesn't make any difference. I am recording it though. I am recording it like I did the last one. How about you?
I got doctor's appointment at 1:30.
So 11 to 1 would be better for you. It's likely I don't think we went the full 2 hours last time. I know we did the first time. Last time, I think we were probably closer to an hour and a half at the most. There's not as much stuff. Okay, you can't go either way. So unless you quit your job, let's stick with, because if you can't go, let's stick with 11. And again, I'm going to record it anyway.
I just want to say,
Oh.
for the recording, sometimes I go back and watch, just take extra stuff and review myself. Sometimes you leave it on when you record, you leave the screen on the quiz, so I'm not able to see when you're writing on the board.
Yeah, the problem is when I have this and I'm doing the writing over here, you can't see it. So it's sort of a little of both. So for now, you guys are going to do this. Now, I'm giving you N, X bar, and S. I could ask for a confidence interval for mu or sigma, couldn't I?
Yes.
I asked for sigma. And by the way, this is the exact same question I asked on the previous quiz, but I used mu. And there's a reason I did that, to show you that, oh, you know what? You're starting with the same information. It's up to you to figure out which part of it do I need to answer the question. So in this one, what do I need? I need the N, I need the S, and I need 95%. Because the 95% tells me which columns I'm going to use. The N tells me which row I'm going to use.
Okay, there we go.
So what are the degrees of freedom in this problem? If you're thinking about it, you're doing it wrong.
Okay.
You can't think about what's degrees of freedom.
Oh.
What's degrees of freedom?
N minus 1,
So this problem is
24.
yeah. Degrees of freedom is one less than the same size. That's, yeah, some of you walked in late. We spent the first probably 20 minutes of class explaining what that was and what it meant. Now, that tells you the row.
Yes.
The columns come, I need which columns give me 2.5% tails, one at each end. Well, the right end's easy. I'll look for 2.5%, 0.025. I'm going to give you a little hint.
Wait a minute. Okay.
95% confidence interval means I have 2.5% tails. You're looking strange. We've only been doing this for like 2 weeks now. Confidence interval. It doesn't matter what I'm doing confidence interval. If I have a 95% confidence interval, it means I have 2.5% tails. Now, which column has 0.25 in it?
Oh,
Now,
that's mine.
so without even thinking, the third column from the right is one of them. So what's automatically the other one? The third column from the left. Remember, they match.
Oh, yes.
Is your point
They have to go in like
Yes,
that.
they go together. Now, here's how you know. You asked this question earlier. I have a 975 and I have an 025. Those two numbers add to 1, and their difference is 0.95. Perfect.
So we're using it at 7.5?
That's one of them. And what's the other one? Yeah, because
I was looking at that one, but that's what 95%.
nope, and you never use that because then you don't have another tail. Remember, you have two numbers you gotta look at, and the whole tail has to be. Oh, that's your chi-square. Oh, okay, so, hold on, so 24, no, you're asking that problem. So it looks like, yes, those are the two numbers you're gonna use.
Okay.
Now the formula, it's on the formula sheet. I've written it on the board a few different times. What is the formula you're going to use? It's the n minus 1 times s squared over the chi-square.
Which one were you to?
Well, I asked you for sigma, so you're going to take the square root of it. And by the way, it makes it easier if you just start by putting the square root on it. Then you just enter it in your calculator that way. And you guys, when we did that a few minutes ago, you guys did a really good job of entering it correctly. And that's important. You want to know You know, when I do this, I know I got the right answer.
Uh-huh.
And again, if you have a calculator where you can see the display clearly, maybe it takes longer to enter, but I think you have way more confidence in your answers because you can see what you entered. Like I like Rosalind's calculator. It's more work to enter it, but now you have no doubts at the end of it, right?
Mhm.
Which one are we using? Right? This one? Yeah. Now I asked for sigma, that means square root of everything.
You want us to add?
Now that is, what is that one? That's the whole thing?
I just have to start with it.
So did you divide it by zero?
Yeah.
Okay, so it's the square root.
No, I just wrote it. Okay.
Yeah, no, you don't have to re-enter.
I know.
Just hit square root answer. Yeah, yeah.
Oh, did you just go?
So,
But I'm sure.
have a big number on the left,
Oh.
because
Okay.
smaller denominator means bigger quotient, so
Okay.
it means you gotta
Swap
flip
them?
them around,
And
yeah.
then in the parentheses, I'm confused.
Oh, that's your S squared.
This
So if
one
I gotta,
goes here.
I gotta square this, that's what's going in the parentheses.
Oh, okay.
The square this, because it's S squared.
No,
remember?
Okay.
Well, you're gonna round the square root.
What numbers?
Yeah.
It's-
But it shouldn't be that long.
You just look at the square root button on the calculator. So you don't even need to write that. Just like the square root. You want to try. Right. And then tell me what the whole thing is. You're doing the whole thing on the calculator. You don't need to tell me each individual piece, just tell me the result. Because otherwise you're telling me, okay, let me write down what the square of that is. Now let me write down the product of it. No, just the whole thing's on the calculator. So it's the result that's important. I know, I keep getting.
This, the equation part of it. Because my phone does, so those are the equations.
All right, are we getting somewhere? Nyla, are you getting this?
Yeah.
Well, if that's that number, that's that number, then that would be sigma squared, wouldn't it?
Yeah,
So you want to do the square root of each of the six.
okay. To get,
If that's true, then to get sigma, I need to do the square roots. We just did that a moment ago.
I did it.
Did you get something incredible and wonderful? Yep, that's what you look like. Now, here's the simplest check on planet Earth.
you always square root?
Well, no, you got an answer. What was the S?
12.61.
Is that number in your interval?
Yeah.
That's a good sign, by the way. In fact, here's an absolute always true. The interval that you just gave me for sigma, you went from here to here. This number has to be in that interval. And I said, which should it be closer to, the smaller number or the bigger number? It'll always be closer to the smaller number because remember, because it's open-ended. So when you're all done, remember when we set up a confidence interval for P or a confidence interval from U, our sample was always in the middle of the confidence interval. That's where we got it. So our S ought to be in the middle of our confidence interval, but because it's not a plus or minus, it won't be smack dab in the middle. It'll just be in there. What'd you get?
So this one.
What's 87.3? That's, okay. You're doing something completely whack. This isn't involved in any conceivable way in the problem.
Oh, you know what?
The formula has an S squared in it, not an X bar.
That's not.
Yeah, go back to the formula and you get something, you're doing crazy now. So, maybe it's a little too small. Oh, you got to square that.
Oh.
Yeah, this is, that's right, that's your denominator. That's S and the formula is S squared. Yeah, guys, don't forget, I'm giving you S, but the formula has S squared, so you got to square that number. So you got to square it. S,
See, that's why I asked them, like, right?
so S squared is,
Which one are you?
so you gotta do that.
Okay, and then.
Yeah.
Got it.
And by the way, Raj, you know why you know it's not right? Because 12.61 does not fit in that interval, does it?
That's true.
That's why I said that's the ultimate check. The ultimate check is, does S fit in the interval? If it doesn't, it's not true. Okay, I'm gonna leave this one, I'm not gonna, you guys can do the second one on your own. I'm gonna leave this one there. Because if you can do this one, you probably can do the next one.
Yes.
Yeah, you guys are all making the exact same mistake. The formula is n minus 1 times s squared over chi squared. Therefore, you need s squared in the formula. That's s. That's not s squared. That's s. That's not s squared. So you got to square that. Now, in a previous example, I gave you s squared, so you didn't have to do it.
Okay.
But I gave you s, so you got to square it.
Okay.
So you're tricking us, then.
No, I'm trying to give you every look so that you don't get tricked. Because getting tricked is below average, right? Okay, so in a 99% confidence interval,
And
then don't I have a 0.5% in each case?
Right, so you take this.
So
and
there's
this.
there's a 0.5%, no, that's 5%.
Oh, yeah, we did that one. Oh, that's a half.
So I take that one and that one.
Got it.
And the difference between 995 and 005 is 0.99, which is 99%. That's how I know I did it right.
Thank you.
Can you believe I made a square a number with a calculator? Oh my goodness. That's crazy. All right, except you're close in the wrong direction.
But with the square.
Probably, but that number should be first. Now, is 12.61 in your interval? Is it- Yes, and that's a good sign. If the given value is not in your interval, then the interval can't be correct. Because remember, you're using 12.61 to create your interval.
I don't need
Now, how could I
that.
make,
I use my mom's.
generally speaking, we like intervals to be small because, we don't like huge cushions. Do you agree? And I said, the only thing you ever have control over, you have no control over results. You only have control over sample size. So the rule of thumb, if you guys stare at your table for just a moment, just pick a column. I don't care which column you pick. Just pick a column. Just pick the first column. What happens to numbers as you go down? They're getting bigger because the variance should get bigger the bigger the number.
That's true.
But that also means your denominators are getting bigger. So what's happening to quotients when denominators get bigger? Don't quotients get smaller? So the bigger your sample size, the smaller your range of values is going to be.
Okay.
And we always like smaller ranges of values than bigger ranges of values. Okay, now that number is in this interval and it's closer to the small number. That number is in this interval and it's closer to the small number.
Okay.
Now, what I would do is I'd skip that one.
Yeah.
Because you did the whole thing on your calculator, right?
This is before.
Oh, okay, okay, yeah.
It's my answer for that.
Now, quick check. Is this number in that interval?
Yes.
It is. And it's a little bit closer to the first value, which is always the case. It should always be a
Okay.
little bit closer. So that breeds confidence.
Got it.
Now, in other words, when you did the squared, it wasn't going to work.
No, it wasn't.
Is it possible I could have looked up the wrong chi-squareds? Yeah, I could have an interval that's too big or too small. So this is where you go, okay, the chi-squares I'm looking at, I got to go back. So did I get the right columns? And if I did, that's perfect.
So whenever it's this, you have to square it,
Square rooted.
square root it.
Yeah, because remember, the formula involves s squared and sigma squared.
Mhm.
So one is, square or square root, depending which way I go. I had to square my s in the formula, but I wanted sigma, so I had to take the square root of my result. So just be mindful.
Is there just one?
It's either s and squared. It's either sigma squared. Okay, I know how to go back and forth, square root or square root, depending.
Thank you.
Okay, so tomorrow we will stay at 11. I will send you which link we will use, so you don't have to worry about it. I think that, does you guys remember what we used last time?
Tuesday.
I probably have to use the Tuesday link because it kind of goes week by week. And after today, we will have used the Thursday link. So I don't think I would have access to this link. I would have access to the following Tuesday. I think that's why we have to use the Tuesday link.
Okay, so 24 times the square root of
I did it.
4.61 over the 39.374.
That's not the numbers other people are getting. Now, the easiest way to do this, square root parentheses.
Use the
That
one.
times that squared divided by that close parentheses. Try that. You might be making it too complicated, but you have to have the entire thing. 24, why 24? Oh, I'm sorry, you're on this one. Sorry, you're on the next one. So, and then 12.61.
For the second one?
No parentheses. No, just times 12.61 squared. You're going to square root divided by that number. Now close your parentheses. That's not the same number. But that's what it's supposed to be. Now, is this in this interval? And is it closer to the first number? Then that's probably a good sign. The only question is, did you look up the right chi-square numbers? That's the only other thing. So that's, again, the simplest check on planet Earth is S in your interval. And is it closer to the first number? If it is, then your answer makes sense. And the second question is, did you look up the right chi-square numbers?
You're smart.
Well, at least he pretends to be, right?
Oh, you know what? Yeah, I think this one of my things.
Yeah.
There we go. All right, so the second problem is identical to the first problem in that I gave you X bar, S, and N. I'm asking for sigma, so there's a square root in there somewhere. But now a 99% confidence interval, so make sure you're looking up the correct chi-square numbers. And like all the previous confidence intervals, this comes down to just, did I look up the right number? If I did, the rest of it is just calculator button pushing. It's all about the button pushing. I have a plethora of quizzes here. You were asking about them the other day.
I turned in the ones that I haven't taken yet. They're in the file.
If you have a quiz for me, I would really appreciate it. We're gonna wrap things up soon. So now you
Into the both ends.
after, so I looked up
Yes.
these numbers.
And I'm
After row of 50.
I did that. I did that. Oh,
You have two numbers.
oh, okay, that's what I forgot.
Now remember, when you're writing it, bigger number goes on the left hand, smaller number because you want your inequality.
Okay.
Okay.
Oh, that helps. Hey.
All right, I'm not going anywhere if you guys are sticking around for questions, because we're basically done with class, but if you have questions. So I'm gonna go ahead and stop this.
Oh, Mr. Brown,
Sorry, do you have a question?
I just wanted to say that I will not